So as I mentioned at the end of the last video, you can also use conservation of energy method in order to derive the equations of motion for a rigid body system under the following circumstances. So for instance, your system must be conservative, right? We discussed this last week. So only conservative forces can do work. You also need only one rigid body and 1 degree of freedom. And if that's the case, then you can use the fact that kinetic energy plus potential energy is constant for a conservative system, which then gives you that the derivative of the sum of kinetic and potential energy is equal to 0. Now, in this example here, you see that we have 3 forces, mg, F1, and F2. F1 and F2 are non-conservative. However, they're acting at this point O, which is, as we talked about in one of the prior videos, this is the instantaneous center of rotation. And now by definition, this point does not move, right? In other words, these 2 forces, F1 and F2, do not do work. The only force that does work is the gravitational force mg. Therefore, the system is conservative, and so we can go ahead and use this method for calculating the equations of motion. One thing to note, though, as the only difference when you have a rigid body is that the kinetic energy is equal to the following. We have 1/2 mass times the linear velocity, right? So our v of the center of mass of our rigid body in frame A squared. Now we also have to consider plus the energy that's coming from, so we have 1/2 times the moment of inertia of the center of our rigid body with respect to the center of mass times our angular velocity here. So you have to consider the angular, or the energy, kinetic energy that's coming from linear motion and from angular motion. Okay, so let's go ahead and plug this in. So for kinetic energy, we have 1/2 m, and then you should remember from the last video that our velocity of the center of mass is equal to d theta dot over 2 times b2 squared plus 1/2, and then our moment of inertia about the center of mass is m over 2 times capital D plus lowercase d squared. And then we multiply this by our angular velocity, so that's going to be 3 squared. And then this simplifies down to, we get 2 md squared theta dot squared over 16, plus we can write this as m d squared plus little d squared theta dot squared over 16. So we end up with 3 md, sorry, we get 3 m 3d squared plus little d squared over 16. And so for potential energy, we first have to define our reference point. So we're going to say that our reference point, so where we have 0 kinetic energy, or so, I'm sorry, 0 potential energy, right, is when the disk is oriented like this, so theta is equal to 0, and our center of mass is located here, and so this is D2. And we've gone over this before, so what that means is that our potential energy is equal to mg and we're going to have d over 2, 1 minus cosine theta. And that's because you can write the location in the A1 direction of the center of mass of our system as d2 times cosine theta. All right, and so now we add these two together, right? So we have, and we take the derivative, so we're going to get, we have m 3d squared plus little d squared over 16 plus mg d over 2, 1 minus cosine theta, and that's equal to 0. And so when you take this derivative, you end up with, oops, I forgot a theta dot squared term. All right, now, so when you take this derivative, you end up with 3d, so you have m 2 and 3d squared plus d squared, and then you have theta double dot theta dot over 16 plus you have mg d over 2 sine theta dot is equal to 0. And then we can get rid of this m term, and we can get rid of this theta dot term, and we can write this as, or we can get rid of this half by multiplying everything by 2. So let's multiply that by 2 here and by 2 here. So that gets rid of those terms. And so now we write this as, so 4 over 16 is just going to give us a fourth. So we get 3d squared plus d squared theta double dot over 4 plus g d sine theta equals 0. And I know it's kind of crammed in here, but this is, again, the exact same equation of motion that we calculated using the other two terms. So again, if you have a conservative system, you can feel free to use this method. The only difference is that you have to remember to include the kinetic energy that comes from rotational motion.